So the plan was not to make one of these for this lab because it's mostly math, but Dr. French looked sad when I said I wasn't gonna do it. So now I have to do it. So this is it. Get ready. How do you pronounce the thing? We're gonna be looking at sluices. Would you mind to speak a little bit about what you've done in Excel?
So I've set up all the equations that we're about to collect with the data. Everything that we're collecting is in millimeters, so there's a few unit conversions that I have to make. And then there's a few if statements I had to make to figure out if the flow number is critical or not.
Have you ever done something like an if statement in Excel before?
Yes, I have, but this time I had to put an if statement within an if statement, which I have done before, but always fun to do that again.
Jumped in front of him.
Yeah.
We've never seen the term wetted perimeter before. Could you tell me a little bit about that?
So the wetted perimeter is the channel width, so it'll be B, plus 2 times the height of the sluice gate that's underwater.
The term hydraulic radius is also new for us. Can you tell me what you know about that?
It's going to be the flow area divided by the wetted perimeter, which is what we just learned.
Can you tell us a little bit about the critical depth?
When a sluice gate is like in place, upstream of the sluice gate, you're going to have what is called subcritical flow, where you have a large depth of water, the flow rate is low. Downstream of the sluice gate, you're going to have a lower depth of water, and the velocity is going to and the flow rate are going to be higher.
There you go.
So where that transition period is our critical depth, or Y sub C.
To this kind of fluid flow stuff.
Can you tell us a little bit about Reynolds number?
In fluid mechanics, Reynolds number help you predict the fluid flow. So when you have low Reynolds number, that's an indication of laminar flow is building up in layers, incrementing layers. And then if you have higher Reynolds number, it go more like mixing. That's like a turbulent flow. So it go more chaotic in comparison.
We haven't seen Froude's number before. Could you tell us a little bit about that?
Froude's number is a measurement of bulk flow. It is the water velocity over the square root of gravity and the hydraulic depth. It's a ratio to find if a flow rate is supercritical, critical, or subcritical.
A conclusion that we were able to make in this lab, and also something that we've been learning in class, is the water that has the faster velocity is caused from the water that has a higher height and pressure upstream. Even though the water upstream has that block, it's not gaining or losing any height. So the water downstream must have a faster velocity because it has less of an area to get through. So, yeah. This is also shown in our graph comparison with weir height and flow rate. The two that have them on different axes. They show a almost linear but definitely positive correlation, which makes sense because, you know, the more area you have, the more water that can get through.